Hey everybody, how's it going? So in today's video, we're going to cover some common reactions seen in a typical um, undergraduate level organic class. Um, it's going to be in no particular order. We're going to just kind of go through all the common ones that I have listed here. We'll take a look at some of their mechanisms. We'll point out what reaction type, they are. Is there any cell activity? Is there a workup step? What is the conditions? What are the reactants, the reagents? Um, and what are the kind of mechanistic summaries and the steps in the reaction? Okay, so it's going to be an interesting one. We'll try to organize this on the video kind of description so that we can have you kind of go over the title cards of each one. But without any further ado, let's get right into it, okay? So one of the first reactions I would like to take a look at is electrophilic addition to an alkene, okay? And so specifically, I will write down here one, and that's, kind of get rid of this. So here it is. So we can have electrophilic addition of HX to an alkene. What is X? X can be any halogen, so something like Br, something like Cl, iodine, okay? In this case, we're just going to kind of do an example with HBr, okay? So what does the kind of mechanism look like? Well, if we have something like this alkene right here, okay, so let's do this. How would this alkene, how would we add HBr to it? So here's my HBr, and boom, okay, and I will get Br right there. And there you go. Okay, so this is the electrophilic addition of an HX to an alkene. How do we know this works? Well, you have to remember that there are, so this is a methyl group, this is a methyl group, and this, of course, is a hydrogen, and this is a hydrogen. But the pi bond of this alkene will, it is our nucleophile, okay? And this right here, this HBr, this is delta negative, this is delta positive, and so this proton here is our electrophile, and so we know that in any polar kind of reaction, electrons will flow from a nucleophilic region to an electrophilic sink, and this is what happens, okay? So here's my nucleophile, here's my electrophile, and it will grab this proton, and so we call this a kind of a protonation step, right? And at the same time, the bonds between the hydrogen and the bromine will have to break. Why do they have to break? Because, of course, bromine, hydrogen can't make more than one bond, right? So if it's going to be bound to this structure, it can't be bound to the bromine at the same time. So that's why we'll have to break its bond. Now, why does the bromine take the electrons? Because bromine is the more electronegative atom between these two. And so, of course, it will kind of hog the electrons with itself. And that produces this structure, this intermediate structure. We usually depict that by brackets. Now, how do I know that there is a positive charge here? Well, again, you have to remember that there are hidden things here. So there is our hydrogen that we had here. There is the hydrogen that we had here. And now you have to remember, we actually add this new hydrogen here. Okay, now, you might be asking me, why do you add it here and why not here? In this scenario, it doesn't really matter which side we add it in because this molecule is symmetrical. But if there were other examples where there is an asymmetry, then it will matter. And we'll come across some of these examples. But for now, just trust me. And so, in this case, we add a kind of hydrogen here, and sorry, we add a hydrogen here and the plus charge is here, okay? And if the plus charge is here, then, and let me depict this kind of better, we will attack this carbon, okay? And we will get this. Again, there is a hydrogen there, and there's two hydrogens here, okay? So this will become my product, okay? So I hope everything is clear here. Of course, anything to do with mechanisms, we have to draw an arrow from a region that has electrons, such as a bond or a lone pair, and the arrow ends either at a bond or at an atom. So in this case, we ended at an atom, but you can also end at a bond, okay? Again, we'll take a look at that. Never forget your formal charges. They are very important, okay? And yeah, there you go. So again, in this step, our pi bond was our nucleophile, our proton was our electrophile. In this case, we have what's known as a carbocation intermediate, and our nucleophile is the bromide ion, and the electrophile is our carbocation carbon. And so you can see that nucleophile will always have an arrow going from a nucleophile to an electrophile. You will not have an arrow from an electrophile to a nucleophile. That is absolutely incorrect. You have to have the arrow from a nucleophile going to an electrophile, okay? So this is the reaction of the electrophilic addition of HX to an alkene. So one more time, it is a Markovnikov addition. What the hell does that mean? So this is Markovnikov. And what that means is that the addition occurs to the less substituted carbon. Okay? So again, in this case, it doesn't really matter because, again, both of their substitution patterns are the same. But imagine that I had done kind of this. So instead of a hydrogen, there was another methyl group there. And in this scenario, if this was the molecule that I was starting with, then the hydrogen will add to the less substituted carbon, and the plus charge will develop on the more substituted carbon. And there is a reason for this, which we'll talk about. It's due to something called carbocation stability. Okay, so again, we can have carbocations that are tertiary, we can have carbocations that are secondary, and we can have primary carbocations. Okay, so this is a primary carbocation. And carbocations are usually more stable the more electrons donating groups they have around them. So in this case, there is a whole bunch of electron donated groups right next to this positive charge, and they will be stabilizing this positive charge by donating electron density to it. So, of course, a secondary carbocation would be much more stable than something like a primary carbocation that would develop here. And of course, we always want to develop the more stable product. And so this is what we will do. Okay? And so, again, we say that this is Markovnikov, meaning that the substituent will add to the less substituted carbon, and the halide in this case will add to the more substituted carbon purely because of the carbocation or the positive charge that develops there is more stable. Now, do understand that Markovnikov addition has nothing to do with carbocation being there or not. You can have Markovnikov addition without the presence of a, carbocation forming or not. But in that case, those are just different reasons that lead to this Markovnikov addition, okay? Now, because the reaction has to be done in a specific way, meaning that because this substituent has to be added specifically here and not here, we say that the reaction is what we call regioselective. Okay, so the reaction is actually regioselective, all right? Meaning that you get a specific regioisomer, All right, regioisomer refers to a specific constitutional isomer of a molecule that you get out of a reaction. Okay, so this and this are exactly the same chemical formula. These two are both the exact same chemical formula. The only difference between them is that in this molecule, the Br is here, and in this molecule, the Br is here. And that is purely because of the way they added onto the molecule. And that means that they are constitutional isomers of one another. And so whenever a specific constitutional isomer is produced throughout the reaction in more you know, concentration than the other, we say that that reaction is regioselective because it is producing this one specific kind of regioisomer. Okay, so that is the first reaction we're taking a look at, electrophilic addition of HX to an alkene. And this is an amazing kind of reaction for generating an alkyl halide. Okay, so take a look. We have now generated an alkyl halide from an alkene. All right, so that is important. So I do want to take a step back very quickly and tell you guys all the reactions that an alkene may undergo. Okay, so here is kind of like a generic alkene. And what are some of the reactions that we'll kind of take a look at here? Okay, so we took a look at the addition of an HX, which can generate for us an alkyl halide. Okay, but you know, we'll take a look at it. There is a way of generating a alcohol. Okay, so we can make alcohols from alkenes. And again, there's many ways of doing it. We can make aldehydes or ketones, aldehyde and a ketone from an alkene. We can make a diol, which is essentially two OHs. In this case, this is just one alcohol, right? And we can, you know, create different kinds of alcohols and diols. Okay, so we can make a syn-diol and an anti-diol. We'll take a look at what those things are. We can make something called a halohydrin. Okay, so it contains both a water and a halogen. All right, substituent on it. Again, we can make different kinds of alkyl halides, you know, by addition of, instead of HX, just by addition of something called a Br2, for example, or a Cl2. We can make just a straight alkane by getting rid of the double bond entirely, okay, and adding nothing else but just hydrogens, okay, so and making a fully saturated alkane. And yeah, so these are some of the reactions we're going to take a look at for alkenes, okay? So yeah, this is kind of some of the reactions we'll take a look at for alkenes. And one of the first ones we looked at of making a kind of alkyl halide is this electrophilic addition of HX to our pi bond there, or to our alkene specifically. Okay, amazing. The next kind of reaction we're going to take a look at is how do you actually make an alkene, okay? So let's say you have an alkyl halide, just like the one that we made here. How can I make an alkene, okay? So make alkene. Okay, so how do I actually make this alkene? Well, let's say that I'm starting with, so let's start off from this same alkene that we made here, okay? So how do I actually convert this this alkyl halide that we made here? How do I turn this back into this alkene? Well, let's do this. Let's draw our nice little alkyl halide that we created, okay? Again, we're omitting the hydrogens as per usual. But I do want to make you understand there was one hydrogen here, right? So let's, for, again, the sake of me proving something here to you, show just that one hydrogen. In this case, we are going to be doing a reaction called dehydrohalogenation. Okay? And this reaction of dehydrohalogenation that is done by alkyl halides leads us to making an alkene. Okay, so let's see how this works. This reaction is something we'll call an elimination reaction, and in this specific case, because it is a secondary alkyl halide, it is an E2 elimination. We'll take a look at E2 and E1 a little bit later in this video, but an E2 reaction in this case will look something like this. This reaction is done with some, strong base like potassium hydroxide. In this case, we're just going to show the OH minus that will come here. It will take this proton, right? And the bonds will flow. The electrons from this bond will flow in here, this alkene, and at the same time, this bond will break. And we will generate, boom, our alkene back. You see, here's that same alkene that I had. I generated it back from eliminating a hydrogen and an halogen, right? Dehydrohalogenation of my alkyl halide. Okay, so you see, this was an elimination reaction. It occurred in a single step. Okay, because it occurred by an E2-like mechanism, or not even like, it is straight up just an E2 mechanism. And yeah, so again, in this case, this is my nucleophile, this is my electrophile, right? He will kind of take this and form, if you want, water as a byproduct. And of course, we will have Br minus as a byproduct as well of this reaction. Why? Because this guy will leave on its own, take the electrons with it. And if you really want, because we started the reaction off with KOH, we know that in aqueous solution, KOH separates into potassium and an OH minus. This is my OH minus, and this K plus at the end of the reaction will associate with this Br minus and make KBr. Okay, so if you want, this is actually the full kind of reaction, right? We will start off with my alkyl halide, and by the addition of potassium hydroxide in some kind of ethanol solvent, we'll say like this. Here's my ethanol solvent. I will actually get, boom, plus water and KBr. So this is actually the entire full reaction, if you're curious. But we just showed the mechanism here for you, and you can see, of course, every single substituent is here, right? So yeah, amazing. And again, this is a single-step E2 mechanism. Now, you might be asking me, how come the electrons flow in here and not here? And the reason, again, lies in the fact that this reaction is regioselective, and it forms what we call the Zaitsev product. Okay, it forms the Zaitsev product. And the Zaitsev product, again, is the more substituted product. Okay, again, I hope all of you understand what I mean when I say substituted. Substituted means lack of hydrogen. Okay, so this guy right here has 3 hydrogens. This dude only has 1, 2, and this guy only has 1. Okay, so again, this specific carbon here is the least substituted section, whereas this, of course, is the most substituted. So again, this specific reaction will generate the Zaitsev product, which, of course, gives you that Zaitsev elimination product. Okay. So in most scenarios, it is also what we call stereoselective. Um, and it is stereoselective in something, you know, let me rephrase this. It is stereoselective because it gives you a trans or the E alkene over the cis alkene, okay? And in a cyclic system, the E2 mechanism is stereospecific, okay? So there is a difference between stereoselective and stereospecific. We're not going to get into it too much, but stereospecific means that essentially only one kind of enantiomer is formed, or diastereomer is formed, but and it's because the mechanism enforces it, okay? The way the mechanism works out is that you have to generate that specific product, okay? It can't be another kind of stereoisomer of that product. Stereoselective means that, okay, the reaction forms both of them, but one is favored over the other. But stereoselective, absolutely not, okay? All right. Now, like I was saying, in a cyclic system, the E2 mechanism is stereospecific, requiring what we call an anti-periplanar arrangement of the beta hydrogens and the leaving group. So, for example, if we have something like this, right, with the bromine here, we know that there is a hydrogen here, okay? And so if I were to do the same reaction, right, this would take the hydrogen, these electrons would go here, and this would leave, and we would generate this alkene, okay? But like I told you, in a cyclic system where we have an E2 mechanism occur, right? An E2 mechanism for an alkyl halide like this usually occurs for a secondary and tertiary. Okay, they undergo this. Secondary and primary undergo E2, whereas a tertiary undergoes E1. All right. Again, this is for reasons that you don't have to worry about right now. We'll talk about it at the end of the video, but it has to do with carbocation formation and the stability of the intermediate. But for now, don't worry too much about it. This reaction is concerted. Concerted means that it all occurs in one kind of step. There is no, intermediate that is formed. But when I said that the cyclic system that performs this E2 is stereospecific and requires anti-periplanar arrangement of the beta hydrogen, that matters because any carbon that bears a functional group is known as the alpha carbon. And so this is the beta carbon, and the carbon that bears this hydrogen is known as the beta carbon. And of course, the hydrogen by that kind of terminology will be termed the beta hydrogen. So here's the thing. If I were to draw a chair conformation of these two, okay, and here's the chair conformation for it. And again, notice I simply converted this into its chair format. Here's our bromine, and here is my hydrogen. But notice there's two hydrogen here, okay? This one's omitted. How do I know which of these hydrogens is going to be taken by my OH minus? Is it this one or is it this one? Well, the reaction mechanism, it literally implies that it has to be the hydrogen that is 180 degrees apart from our what we call a leaving group. Okay? And so because of that, we say that the reaction is stereospecific because, again, the mechanism enforces this. The mechanism enforces us to take this hydrogen and never this hydrogen, okay? And so this specific orientation where they are 180 degrees apart is known as anti-periplanar conformation. And so this is the hydrogen we will be taking. Again, in a mechanism, of course, you will see this, okay? Amazing. Okay. So let's kind of erase all of this, and just to reiterate one more time, this is what we would call a dehydrohalogenation reaction, and it is an elimination reaction. And depending on the substitution pattern, whether secondary or primary, we will have an E2 mechanism. If it is tertiary, under acidic conditions, we will have an E1 mechanism, okay? Again, we'll dig into this a little bit later. The reagents, like we said, we need a strong base, okay? Something like sodium ethoxide, okay? So if you're curious, here is sodium ethoxide, all right? Or potassium hydroxide, sodium hydroxide, doesn't really matter. And a vicinal alkyl halide, right? Again, a vicinal alkyl halide is defined as this exact same thing. You know, yeah, vicinal meaning like they're pretty much next to one another. Anyways, the conditions, like we said, it's usually performed in an ethanol solvent or any other kind of polar protic solvent, and moderate heating may be required. We talked about the fact that it's regioselective, right? It gives you the Zaitsev product. We said that it is also stereoselective because we favor the trans formation. And there is a reason for this because the cis is kind of higher in energy because of steric effects. We said that in a cyclic system, it's stereospecific, requiring that anti-periplanar arrangement. So that's one thing. There, yeah, that's pretty much it. Okay, so the next one is, again, how do I make an alkene part 2, but from an alcohol? Okay, so let's say I have an alcohol, and we'll talk about how we make alcohols, right? We said that is one of the reactions we're going to take a look at. But so far, we've took a look at how do we come back from this alkyl halide to an alkene, and now we're going to take a look at how do we go back from making an alcohol into an alkene again, okay? So again, anytime you want to make an alkene, you should remember that it's some sort of elimination reaction, okay? So this was an elimination reaction, and anytime, again, you're making a double bond, it has to be some form of kind of elimination going on. And so in this case, we're going to do a reaction called the dehydration of alcohol. Okay, and a dehydration of alcohol, again, gets you that alkene by way of an elimination reaction. Okay, so the mechanism is very kind of similar to an elimination. One thing that I actually did forget to mention is that this right here is very similar to an SN1-like reaction. Single nucleophilic, single nucleophilic substitution. So yeah. Yeah, okay, so back to this dehydration of alcohols. Again, let's say we are starting with this alcohol. We have this guy right here. We have an alcohol here. And here is going to be our kind of solvent and our reagents, right? We're going to use aqueous acid, H2SO4 in water, and water. And THF, this is an ether solvent, okay? Here is THF, this is how it looks like, at 50 degrees Celsius, okay? So, again, you need an alcohol starting material, you need strong acid, you could also use H3PO4 here, okay? But it is done in kind of aqueous solution. And sometimes we say it's perform an aqueous THF. Again, this is our kind of reaction conditions. Heating is required, right? 50 degrees Celsius. And you will get this kind of product right here, right? You would generate your alkene. Now, and you, of course, make water. Now, how do I know this reaction mechanism occurs by way of elimination? So, again, you have to kind of take a look at it like this. If I have this H2SO4, anytime you have an acid, protonate something. Okay? Anytime you have an acid, protonate something. So, in this case, I have, and let's show it better. In this case, I have what we call a secondary alcohol. So secondary and tertiary alcohols undergo an E1 mechanism. So in the previous reaction, we saw an E2 mechanism. Okay, E2 occurs in a single step. It's concerted. E1 mechanism occurs in multiple steps. Generally, it involves two steps, right? There is a protonation and then an ionization, then a deprotonation. Okay, and of course, like I said, E2 is for primary substrates. Again, it has to do with carbocation stability. So let's take a look at the mechanism. In this case, I have H2SO4. Here is my H2SO4, right? And again, anytime you have an acid, you're probably supposed to protonate something. And so remember, this is my nucleophile. This is my electrophile. How do I know this? Well, again, this is a delta minus, this is a delta plus, and this right here has extra electron density. And if you want, I can show it to you this way. Delta minus, so of course it will be my nucleophile attacking my electrophile. Let's get rid of these, okay? This will come here and do this. Don't worry too much about what I just did there. That's to kind of balance out that charge and, some resonance stuff. Doesn't matter, but either way, I will protonate this alcohol. Why am I doing this? Well, I'm doing this because I need to make the OH leave, okay? Remember, the goal is to make an alkene, so that OH group, that alcohol, has to leave. And it's a terrible leaving group as an alcohol, but it is an amazing leaving group as a protonated alcohol, which, in other words, is just kind of water. And so when we make this protonated alcohol, guess what happens? It will spontaneously leave now, right? It will take these electrons with it and make neutral water. That's that water over there. And now what's going to happen is, again, if I kind of show this following step, is that's going to make us a carbocation intermediate. Okay, so now, carbocation intermediates, if you remember, I said are more stable as tertiary, and then a secondary, and then finally the least stable primary. Well, in this case, I have a tertiary carbon here, and I have a secondary carbon. Which one do you think the carbocation is going to form on? Well, of course, it's going to be the tertiary because it's more stable, okay? And if this is the case, guess what? I have one proton here, and I have one kind of proton right there, because remember, this was our OH. There's a proton here, and there's a proton here, okay? Now, remember, anytime we're doing eliminations, the product that is formed is the major product, and in other words, it's the more substituted product, the Zaitsev product, right? And with that being said, the way we do that is by abstracting a proton from this guy, okay? And so how do I do that? Well, a water molecule comes in here and abstracts this proton, and the electrons go into that bond. And of course, what do we get? We get our nice little product over here. Okay, remember, we couldn't have done this. If we extracted this proton, the electrons would have gone here, and guess what? This carbon would now be making 10, we'd be making 5 bonds, and carbon can only make 4 bonds, not 5. Okay, so this would be breaking the rules of kind of organic chemistry, and we can't do that. So we make our most substituted product, the Zaitsev product, and here it is. Okay, that is the kind of mechanism for it. And this is the water kind of coming in and doing this and making ourselves a hydronium ion, right? Once it grabs this proton, it turns into a hydronium ion. And essentially, this is recreating our acid catalyst. Okay, so again, remember, this is a acid catalyzed reaction. Um, you know, there's reasons for this, but don't really worry too much about it. Okay, um, essentially, it has to do with the pKa value of water, or really hydronium ion, and H2SO4. Okay, and in this case, it is much more likely that it is actually the hydronium that is being formed as opposed to our H2SO4 again. Okay, so if you're confused about what I said, don't really worry about it too much. Okay, but this is a reaction of how we can take alcohols and turn them into alkenes. Just eliminate. Okay, so alkyl halide back to an alkene, elimination. Alcohol to an alkene, elimination. What kind of elimination? Depends on what kind of starting substrate you have, right? If you have, for example, over here, we had a secondary alkyl halide, then of course we went through an E2 elimination. We said that a primary alkyl halide can undergo an E1 in acidic conditions. Over here, we had a secondary alcohol, and we said that tertiary alcohols can also undergo an E1 mechanism. Why? Because again, the carbocation intermediate that they generate will be extremely stable. Amazing. And of course, we said that a primary alcohol will undergo a E2 mechanism. Okay. All right. Again, this reaction kind of very similar to the previous reaction we took a look at, right? Stereoselective, right? Gives us the E, a transalkene, right? How do I know this is a transalkene? Again, take a look right here. That is trans, right? Not like this. It is not cis. Or, instead of trans, you could say it gives us the E over the Z isomer. Reaction, of course, is not stereospecific. You can get a mixture of the stereoisomers and rearrangement products depending on what you have. But of course, it is stereoselective. You get more than the other. In fact, you'll get like 91% of this and 8% of the less substituted, or what we would call the Hofmann product. Okay, so again, the more substituted is called the Zaitsev product. The less substituted is called the Hofmann product. Okay, again, we'll take a look at this a little bit later. But, yeah. And do realize that because this is, and I mentioned rearrangements, and the reason I say that is because you form a carbocation, right? Okay, so let's move on to our next reaction. So beforehand, we were kind of talking about how we can make an alkyl halide, and there are other mechanisms. So on top of making an alkyl halide that just has kind of one halogen group on it, we can actually make a dihalide. Okay, so we can make a dihalide. All right, and the way we do that is by addition of something like, for example, Br2 or Cl2, right? So let's take a look at the mechanism of how this is done. So here is our kind of other reaction, right? What are we at right now? Okay, so we can take a look at this. I just want to see if that is kind of what we did. Yeah, that's fine. So how do we go about making a dihalide? How can we make a dihalide from an alkene, and that's by a process known as halogenation. Okay, so halogenation of an alkene, or in other words, addition of X2, is extremely, um, you know, useful to us here because, well, you'll see what I mean. So let's take a look at an example. We had, let's do this. Let's take a look at this kind of pentene here. And let's say that there is a double bond there. So what's going to happen here is that we're going to have our Br2. Okay, here's my Br. Same thing. This is the same thing. We're just showing their bond. The alkene is going to act as a nucleophile, right? It will grab this kind of Br. At the same time, this Br will attack this area here. And the bonds are going to have to go to this Br, the bonding electrons here. Why? Again, bromine is not going to be making 3 bonds at the same time, right? So let's see what this is kind of going to get us. This gets me a weird intermediate, right? Remember, alkene was making a bond with the Br. Br was making a bond with this carbon. And so we're going to get this weird structure here that has this plus charge, okay? If you don't believe me, you can go ahead and run the formal charge calculation yourself on this. But it's interesting because it will kind of go ahead and do this. And now what we end up getting is this intermediate called the bromonium ion intermediate. Okay. Again, we depict intermediates in this bracket. Now, what happens to this Br minus that left? Well, this Br minus, if you take a look at it, will do what we call a backside attack. And, in this case, again, in this specific case, it can either attack here or it can attack here. It doesn't really matter in this case. And if it attacks there, it's going to end up opening this little bromonium ion ring and transferring the electrons from this bond into this bromine. And so now what that's going to do is it's going to create us this molecule, right, where one bromine is essentially kind of pointing up on the ring, and the other is pointing down on the ring. Okay? And the reason why this dude is pointing up is because he attacked from the top side, the top face. Remember, this alkene is sp2 hybridized. sp2 hybridized have kind of this flat geometry. And so imagine this guy is attacking on top of a flat surface. This dude is at the bottom of that flat surface. Now, you might be saying, why does he have to attack from the top and not from the bottom? Because the bottom is very kind of hindered. It's shielded from attack, if you will. And so he has to kind of attack from the top side. And in this case, he does, and he attaches to the top, and this guy attaches to the bottom of the ring, okay? And what I generate is a trans dihalide or dibromo alkyl halide, okay? Or in this case, cycloalkyl. Now, it is an addition reaction, this reaction, okay? It has that bromonium ion, or if you want to be more general, it has the halonium ion. Notice how I just kind of replaced the halogen, the specific halogen bromide in this case, with halonium. The addition occurs anti, meaning that the two groups are on opposite faces of the molecule, okay? So it's anti-addition. That is important. And because of this, it is stereospecific. All right. So again, the reaction occurs in a stereospecific manner, right, by anti-addition through a halonium ion, giving exclusively a trans dihalide product. In this case, the regioselectivity is not an issue for us because this is a symmetrical alkene. For an unsymmetrical alkene, the halogen could add to both carbons. Um, and no regioselective preference exists. Okay? So, again, it is important to understand that we form a trans vicinal. Vicinal just means that they are adjacent to one another, so that we would write that as 1, 2. Dihalide. So transvicinal dihalide, again, vicinal meaning they're adjacent to one another. Okay, so a mechanistic summary would be halonium ion formation and nucleophilic attack of the bromine to give us the trans dihalide. All right, amazing. And it is anti-stereochemistry. That is very important. So that is how you make a dihalide, okay? So we covered that reaction very nicely now. The next reaction we are going to take a look at is going to be that formation of what we call a halohydrin, okay? Otherwise also called a hypohalous. So a halohydrin, remember, if I told you that it has a water and a halogen, okay? As the name suggests, halo, right, for a halogen, and hydrin for that water. So how does this kind of, reaction look like? Well, if we had a alkene as we had before, let's do our same kind of transalkene. If I were to normally add a Br2 to it, what would happen? Well, if I add just a Br2, guess what? This would make our halonium ion ring, okay? And in a subsequent step, the Br will undergo nucleophilic attack and generate our Br. Okay? So why is it that in this specific reaction of halohydrin formation, this doesn't occur? Well, it has to do with what we do our reaction in. So this specific reaction is done with Br2 plus, and this is the kicker, it's done in water, okay? So the reagents include an alkene, Br2, and water. Now, Br2 is very hard to work with, and so sometimes you might actually see, instead of Br2, we work with a kind of a bromine donor, which is known as NBS, so N-bromosuccinimide, and NBS in aqueous DMSO, okay, so in aqueous DMSO, which is just our solvent, breaks down to give us Br2, okay? So it is kind of like our halogen source. Okay, so amazing. Now, in this case, because we're doing it in water, we're not going to get this nucleophilic attack being done by bromine. Instead, we're going to get the nucleophilic attack being done by water, okay? And so let me kind of show you the mechanism now that we know this. We will still have the same kind of Br, right? We will still make our bromonium ion ring, right? Boom, boom, boom. Here's my bromonium ion. Don't forget the plus charge. But instead of the bromine attacking, instead, now the water is going to attack, okay? And the water acting as a nucleophile will attack this carbon here, open up the ring, and guess what? It will form this Br here, and it's probably best to draw it like this. But now I have a water over here. I don't want a water, I want an alcohol, okay, on this specific region. And so, again, don't forget your charges. Another water molecule from this reaction will come and get rid of a water. It will deprotonate, okay? So watch. OH2 will come and grab this, and we will get rid of that. And now we will have our final kind of product, which is a Br and an OH. This is my halohydrin, okay? My halohydrin product. Amazing, amazing. Okay, yeah, halohydrin product. So, you know what we call this? Because this alcohol has a higher priority than bromine, right? The carbon here is known as the alpha, and this is called the beta carbon. And so we say that we make a beta halo for a halogen alcohol. Okay, so this product is a beta halo alcohol. And again, it is the addition of a water and a halogen. And it occurs by way of a Markovnikov orientation and also an anti-addition. So remember, here's the anti-addition. And the nucleophile, when it attacks, again, in this case, it doesn't really matter, but usually the nucleophile, when it's attacking, in this case, the nucleophile being our water, when it's attacking, it will tend to attack the more substituted section. Okay? Yeah. So, one more time, we make the halohydrin, which is the beta halo alcohol. The reaction occurs in a regiospecific Markovnikov manner, meaning that our water, or OH, will add to the more substituted carbon, and the halogen to the less substituted carbon. Again, in this case, it doesn't matter because there's no more substituted carbon. But if we had a molecule like this, or like this, then this OH2 wouldn't add here; it would add there. And again, this is because of electronic reasons that you don't have to worry about. Okay, but this has to do with electronics. Now, of course, the nucleophile will have to attack anti to the halonium ion because, again, there is steric crowding, and it has to do a backside attack because of the orbitals. But again, you don't have to worry about this. It is a three-step mechanism, right? The halohydrin formation, nucleophilic attack by the water, and deprotonation. Okay, so amazing. And again, it is important for you to understand that we could use Br2 and water, or we could use NBS in aqueous DMSO. Aqueous just, again, refers to the fact that there's water involved. Okay. Let's talk about another reaction. This one is called, well, before I tell you what it's called, this one is going to allow us to make another alcohol, okay? So you know how in this case we kind of made an alcohol, but, it had this kind of halogen in it? Well, we can now kind of just make an alcohol without having any halogen in it, okay? So remember, so far in this video, we're going to look at how do I go from an alkene to an alkyl halide? How do I go from an alkyl halide back to an alkene? How can I go from an alcohol to a alkene? How do I make a halohydrin from an alkene? How do I make a dihalide? And again, notice we've done a lot of reactions already. But now I want to know how is it that I actually make an alcohol from an alkene, okay? And one of the mechanisms you're going to learn, or one of the reactions you're going to learn, is by something called acid catalyzed hydration of water, of alkene. So acid catalyzed hydration of alkene, which gives us an alcohol. So again, these are all kind of addition reactions. In this specific case, again, if we were to go with a specific kind of alkene here, let's choose this alkene, and there's, hydrogens that are implied here, but we're going to kind of get rid of that. In this specific case, the water, sorry, not this specific case, the water is just going to add to the carbon-carbon double bond, again, in a Markovnikov fashion. So let's take a brief look at this. It is acid catalyzed, okay? So it's acid catalyzed, meaning that I should have some kind of, either HCl or H2SO4. Generally, this is done with H2SO4, or, you can do it with H3PO4. Actually, in the industry, industrial hydration of alkenes, such as, ethylene, ethylene right here, is, that's not ethylene, this is ethylene, okay, uses H3PO4 at 250 degrees Celsius. So this is not a really useful laboratory reaction, but, nonetheless, it's done in the industry, so it's good to learn about it. So how is this going to work? Again, you need some form of acid. In this case, we're just going to say hydronium ion. The reason we say hydronium ion is because, again, in solution, right, in aqueous solution, which, of course, this would be in aqueous solution, generally what ends up occurring is that the acid H2SO4 is just going to protonate the waters to generate hydronium ion. So again, it's really that hydronium ion doing the work. But, nevertheless, let's kind of show our hydronium. Remember, anytime you have an acid, you have to protonate something. So in this case, we will protonate, okay? And I will generate for myself this kind of carbocation intermediate. Again, why not the carbocation here? Because the tertiary carbocation is much more stable, and so the hydrogen adds here, right? Before, if you can remember, there was 2 hydrogens. Now this hydrogen has added in that region, okay? So the plus charge is developing here. And guess what? A water molecule will attack that section, and we will form this kind of OH2, similar deal as last time. And this is a plus charge. What do we do to get rid of it? Well, remember, anytime you have an acid catalyst, you have to regenerate the acid catalyst by the end of the reaction. And so in this case, we will generate our hydronium ion. Okay. And voila, we have made our alcohol. Let's show it like this. Okay. And there you go. We've made our alcohol. Another way to draw this, by the way, a better way to draw this, is this. Same thing. Okay. And of course, in that process, we regenerate our hydronium ion. Amazing. Okay. So now we have made our alcohol, and, you could name this. This is 2-methyl-2-propanol, right? 2-methyl-2-propanol. 1, 2, 3, 2-methyl, 2-propanol, right? The all is for the alcohol. Amazing. Okay, so look at that. That was a pretty easy reaction, right? What are our conditions? Again, requires concentrated sulfuric acid, okay? And high temperatures, such as 250 degrees. It is mainly used in an industrial scale, not in the laboratory. The product is an alcohol, as we just witnessed, okay? It is a regioselective reaction. Again, it attacks the more substituted carbon. Again, it has to do with our carbocation formation, right? The OH group attaches to the more substituted carbon. The proton attaches to the less substituted carbon. It's not stereospecific. The attack on the planar carbocation can occur from either face. So again, this is planar and this is planar. And the reason I say this is planar, by the way, is because if you look at the orbitals of a carbocation, right, it is quite literally a planar molecule. And I can attack that planar molecule from either the bottom or the top, and that would give me the exact same thing. Okay? In fact, it would give me a racemic mixture. Racemic means there's a 50-50 distribution between the enantiomers I would get. And if I were to analyze my, product by way of polarimetry, it would be, well, it wouldn't rotate plane polarized light, so it would be a racemic mixture. Protonation of the alkene. Yeah, we've already talked about this, right? So we know what the steps are. The step is number 1, protonation, because I have an acid. Number 2, nucleophilic attack of the water. And number 3 is deprotonation of the water attached to it to give us our alcohol, okay? Amazing. So there is actually another way of doing this reaction, okay? So this acid catalyzed hydration, remember I told you that it's, it doesn't really help. It occurs at kind of industry. What is another more convenient way of doing this reaction? And the reason I say more convenient is because anytime you have a carbocation forming in the mechanism, right, there is always a risk of a rearrangement product, meaning that the reaction, depending on whatever substrate you're starting with, your molecule might undergo a rearrangement, and that might get you a product that you don't want, okay? And so how can I avoid a rearrangement? Well, I can avoid a rearrangement by not having a carbocation intermediate, okay? And so the way that would work is by a reaction called oxymercuration and demercuration. Oxymercuration, demercuration, hydration of alkene. This gives me that exact same product. Okay, so again, don't believe me? It gives me the exact same. So let's start off with this again. Let's start off with this, and I will tell you what the reaction kind of consists of first. You would actually get what we call a mercury acetate, okay, like this, and by a second kind of step, you will use sodium borohydride to essentially do a reduction, and that gets you your alcohol. Okay, that gets your alcohol. Now, what does this actually look like? Well, there is 2 intermediates involved. There is an organomercury compound and a mercurinium ion. So remember how we had a bromonium ion? Well, this is kind of similar. We get what we call a mercurinium ion. So let's take a look at the mechanism. This is always done in kind of aqueous THF. But again, let's just take a look at the mechanism very briefly. So here is my mercury acetate. Remember, this is how we wrote it. OAC2, right? The 2 stands for 1 and 2. Okay? If you guys don't remember, here's what acetate looks like. So here's what acetate looks like, right? It is the conjugate base of acetic acid. This would be acetic acid. This is acetate. Okay? Or, if you want the kind of resonance proper, it looks like this. Okay? But doesn't really matter. So this is my mercury acetate. What's going to happen is going to be an extremely similar mechanism. So watch. The nucleophile is going to attack this, and this is going to attack this. Okay? And I should probably show it this way. This is the better way of showing it. There we go. And at the same time, this bond is going to break and come here, and I could just show it this way. Now, what this is going to do is this is going to form us a mercurinium ion intermediate. Okay, so watch this. Boom, boom. Plus charge. Okay, so we have a mercurinium ion intermediate. Now what's going to happen is, like I said, this reaction occurs in aqueous THF. All right, and so aqueous, if you remember, I said just means water, right? So this is what's going to occur. The water is going to attack the more substituted carbon. Again, this is that regioselectivity or regio kind of specificity that we talked about, right? That's Markovnikov. It's going to attack the more substituted carbon. Okay, why? Again, it has electronic reasons. If you're curious, the delta plus charge that is developing on this carbon will be more stabilized by the electron donating groups here. But the delta plus that is developing here in the transition state is less stabilized, okay? So yeah, now we transfer those electrons there to open up the ring, and we get this as our kind of next step. So let's draw this. Let's draw our newly attached water. Let's draw our mercury after opening the ring. Beautiful. Okay, so this is now what we have, right? So remember, this was our kind of mercurinium ion intermediate. Now we have what we call an organomercury compound. Okay, so this right here is an organomercury compound. And in the final step, we're going to use a kind of reducing agent to get rid of the copper, not the copper, to get rid of the mercury bond. By the way, if you're curious, this mercury right here has a 2+ oxidation state because, of course, this acetate is a minus charge. This is a minus charge, and so we need to have a 2+ charge here. Okay? Anyways, this... first things first, let's get rid of this kind of plus charge by way of a proton transfer, right? So we will come here, we will come there, right? And we will have our OH kind of generated in the next step. And next thing we will do is, and I will omit the kind of mechanism for this, is, using sodium borohydride and OH minus to do a demercuration. Again, this demercuration, this specific reduction step, is going to get rid of this carbon-mercury bond, okay? And it, again, reduces this carbon-mercury bond and replaces the mercury acetate with a hydrogen, and it generates this kind of alcohol step. And so now, again, you can see we will have our product, and the better way to draw it, I told you, was boom. Okay, again, prove to yourself 1, 2, 3 carbons still, right? It's there you go. This is it. Sorry, no, never mind. This is it. I got a bit confused there. But again, this is your product, and this is how you do a kind of oxymercuration, demercuration reaction. So again, let's go over kind of our, same things that we usually go over. Though again, the reaction type is an addition reaction. Water adds across the double bond via an organomercury intermediate. It is, the reactants and reagents you need an alkene, you need a mercury 2 acetate in an aqueous THF solution, followed by a sodium borohydride and hydroxide demercuration step. The conditions, again, it's carried out at room temperature in aqueous THF with a reduction step under mildly basic conditions, right? Hence our kind of OH minus. It is regiospecific, right? Markovnikov, we know that. Why do we know that? Because the water attacks at the more substituted carbon, and the hydrogen will then attach to the less substituted carbon. Which of course will be here when we do our reduction step by the sodium borohydride. Again, remember that reduction is a gaining of electron density, and since protons donate electron density, or I should say hydrogens, this will kind of be the thing. And you know, you shouldn't really be focused too much on what borohydride looks like, but if we take a look at borohydride, you will come to understand that the polarization is actually in this direction, and so the hydrogens in sodium borohydride are actually hydrides. They're not protons, they're actually hydrides. They are kind of taking more of the electron density from the boron, and the reason is they're more electronegative. Okay, so that's actually one scenario where hydrogen is more electronegative than something. But anyways. Yeah, you know, we talked about it's regiospecific. It's not stereospecific, right? Because again, the water can kind of attack from either side, and the hydrogen can add from either phase. It doesn't really matter, so it's not stereospecific. The good thing about it, though, is that it avoids carbocation rearrangement, right? As you can see, there is no carbocations involved, and so we avoid a carbocation rearrangement. And if I were to summarize the reaction, we have a mercurinium ion formation right here. We have a ring opening reaction, which is this part. And the ring opening reaction is followed by a demercuration step, so right here. And you know, kind of like a deprotonation of our water, and boom. We're good. Okay? So now, hopefully, you've been convinced that we can make an alcohol very kind of easily, and we can do it by two mechanisms. We can do it by acid catalyzed hydration, or we can do it by oxymercuration, demercuration, okay? And again, in both scenarios, I'm getting the same alcohol. It's just that in oxymercuration, demercuration, I can avoid a carbocation rearrangement, which is amazing for me. And of course, now you understand that from the alcohol, I can go to the alkene by way of dehydration of an alcohol, which is, again, it has to do with an elimination reaction, okay? So hopefully you're seeing the kind of trends here. Let's move on to our next reaction. So I have one more way for you to make an alcohol on its own, okay? One more way. And this is an interesting one, because unlike the other two ways that I have shown you, this one is stereospecific, okay? So the other two ways, which were, you know, oxymercuration, demercuration, and acid catalyzed hydration, they weren't really stereospecific. They were only regioselective, okay, or regiospecific. But the hydroboration oxidation is interesting, because I can have something like this. Something like this. And I can, in THF, add a borane, okay? And get this kind of organoborane intermediate. Again, we'll talk about what that looks like. But it looks something like this. again, I will break down what this means. Don't worry. Here's my organoborane, and then through a subsequent oxidation step by hydrogen peroxide, again in OH minus, I will get my alcohol. Okay, so again, boom, 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 boom. And this alcohol is added in a very specific way. Okay, so let's take a look at why this is the case. This reaction is called hydroboration oxidation of an alkene, of course, and it gives us an alcohol, but it gives us specifically what we call a syn alcohol. Okay, meaning it's added in a very stereospecific manner. So let's take a look at the understanding of this. Here's a BH3. This is read as a borane. Okay, so this is a borane, not the same thing as our kind of BH4 that we had, the sodium BH4. That was borohydride. This is borane, and borane likes to add to our molecule in a anti-Markovnikov fashion. So if you remember, Markovnikov, I told you, has nothing to do with the formation of a carbocation and whatnot. Markovnikov simply means that our substituent adds to the more substituted carbon. Okay? Now, the reason it was doing that was because of, again, in that specific reaction, right, the mechanism involves a carbocation, and so it is more favorable for adding to that more substituted position, or there were some electronic reasons, right? But in this case, borane actually is adding anti-Markovnikov, so that means that it's actually adding to the less substituted carbon, okay? And again, this has kind of important implications for us. Let's kind of take a look at what those important implications are. But remember, this reaction is called hydroboration oxidation. So I'm adding a borane and a hydrogen. Here's my borane and a hydrogen. And I'm doing an oxidation step, which is this step right here. And essentially, all this step is doing is replacing my borane with a OH. Okay? That is all that is doing. So, how do I kind of do this? Well, I'm debating on whether or not I should show you guys the mechanism. Okay, I'll show you guys the mechanism. So imagine, again, let's kind of show you the mechanism for this specific one right here. Let's do boom, 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 boom. Okay? So, again, understanding that which one of these right now is the more substituted carbon. Well, remember, I said substitution pattern. Substitution refers to which one has the least hydrogen, right? Most substituted is the one that has less hydrogen because it has other kind of substituents instead of hydrogen in the place of it. So this right now, this carbon, is the more substituted because this one has one hydrogen, whereas this one has 0 hydrogens. Okay, amazing. So now let's take a look at how this kind of mechanism occurs. Well, my borane, like I told you, here's my BH3, it likes to add to the less substituted. So where do you think this BH3, which by the way will add as a BH2, will add to? This one or this one? Well, obviously it adds to the less substituted, so this one. So let's kind of draw our borane in this way. Where I have my borane and I have my H and H, and you know what? I like to do this, really kind of show you guys that orientation that I was talking about. And what's going to end up happening is that these electrons in this guy will attack our borane, okay? And the electrons in this will attack that guy. Okay? And so the borane will end up adding to this carbon, and the hydride will end up adding here. Perfect. So what will this get me? This will get me this intermediate. My organoborane, if you will. BH2. And don't forget there is a hydrogen there now that has been added. So this is my organoborane, just like we had here, organoborane. And remember, this occurs in THF. It's because the BH3 and the THF kind of stabilize one another. You know, they form what we call an adduct, okay? You know, we don't got to kind of go into more details, but it is always done in THF. Instead of, you know, BH3, you could also use dicyamylborane. So dicyamylborane is used for more hindered substrates to kind of direct, not more hindered substrates, but it is used if you want to direct this borane to a specific region, okay? But, you know, neither here nor there. So, okay, now that we have this kind of borane added, let's give it some stereochemistry. Because it adds from this kind of, you know, specific top face, okay? Again, remember, this is a planar molecule. It's adding from the top face. And so we were going to kind of give it this orientation. And of course, this will have that same orientation because they add from the same face. The stereochemistry is set here. Now let's talk about our oxidation step. The oxidation step requires this OH minus to be present, okay, mildly basic. So watch this. Our OH minus is going to kind of activate, if you will, our hydrogen peroxide. Okay, so it will kind of take this away, right, and kind of add here. And now we will have, from this, water produced and an activated kind of, you know, OH minus here. Beautiful. And so now what this guy is going to do is he's going to attach himself to our borane, okay? And that is going to form this intermediate. Okay, boom, 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 boom. H2 with the O H like this. And again, don't forget your charges. Now what's going to happen is that this will kind of leave. Okay, this will go and transfer here. Or sorry, this will transfer here. This will transfer here. Okay. And next, we are, again, don't forget your stereochemistry, right? I'm not showing it, but you know it's there. Next, we're going to get, again, our alkene, running out of space here. Is going to now have our oxygen there. Bound to a BH2. And if you're a little bit confused, it's because this bond, we did kind of like a shorthand mechanism. We depicted that this bond is going to now bind to this, okay, and this is going to leave. And so now we're going to have oxygen bound here with a BH2 bound to our oxygen, and this is now leaving, okay? So that's, again, it's a shorthand mechanism, but, you know, it suffices. And now that we have done this, what we are going to do is we're going to grab this OH minus that we generated here. Okay. We are going to attack the boron and grab these electrons and put them on this dude right here. Oh my God, let's again kind of move over. This is an ethyl, this is an O minus now, okay? And this O minus is going to attack a water that we generated a couple steps back. Okay, so here's that water that we generated a couple steps back. He will attack this, and boom, we have now formed ourselves a alcohol. Okay, so it is a little bit of a lengthy mechanism, but we have formed our alcohol, and it's a syn alcohol. It is stereospecific because it added in a very specific manner. So yeah. And you know, that's pretty much it there, with that kind of specific reaction. Okay. So hopefully that one is not too bad, but again, it's a concerted syn addition of the borane, meaning the borane adds in one step, as we can see right here. All of the borane added in one step. It's concerted. Then, of course, the oxidation steps are separate, right? It occurs in, you know, 2 or 3 steps. And it occurs under alkaline hydrogen peroxide conditions. We used OH minus. Yeah, it is regiospecific because, again, the OH attacks the less substituted carbon. It is stereospecific. The boron and the hydrogen add syn to the double bond, and the oxidation step retains the configuration of the previous step. So the overall addition is syn. And so we can really summarize this reaction as a hydroboration portion, which is concerted, and then the 2-step oxidation, which is first the addition of the peroxide, and then the hydrolysis of the borate. Okay, and there you go. There you go. Next reaction. So again, I'm hoping that you're keeping up here, right? We've taken a look at alkyl halide formation. We've taken a look at how we go from an alkyl halide to an alkene. We've taken a look at halohydrin formation and how we go from an alkene to an halohydrin. We have talked about dihalide formation. We've talked about alcohol formation. 3 methods of forming a singular alcohol, right? We have acid catalyzed hydration of an alkene. We have hydroboration oxidation, and we have oxymercuration demercuration, right? With hydroboration oxidation giving you a syn alcohol, okay? So again, you have many mechanisms under your belt. And alcohol, going back to an alkene, we've also taken a look at that, right? That's called dehydration of an alcohol by an elimination reaction. And we said that anytime you form a double bond, it has to be by some form of kind of elimination. The next reaction I'm going to kind of get you guys to take a look at is forming an alkane. So a saturated alkane can be formed from an alkene, and it is done by use of a metal catalyst. And I'll tell you there's 2 methods to do this. We'll take a look at the other method a little bit later. Or actually, maybe not. Maybe I'll just show you right now. But let's kind of write down number 9 is alkane formation. And you know what? I'm gonna change my answer here. I'm gonna say cis alkane. Or not cis, syn alkane formation. Okay? There is another kind of method to do this, and we will take a look at it. I think we will take a look at it. Just give me a second. Let me kind of take a look at all of these. Okay. So no, this is the only kind of version we'll look at. Actually, this is wrong. I was thinking of something else. Just alkane formation. Okay, just alkane formation. I was thinking about alkynes to alkenes. Forgive me. Okay, let's take a look at this. So this reaction is called a catalytic hydrogenation. Hydrogenation. And if you remember, I told you that it requires a precious metal catalyst. And the precious metal catalyst can be anything such as palladium on carbon. It could be platinum dioxide, or it could be something like nickel. Okay? But the reaction occurs at ambient or room temperature and pressure, or sometimes slightly elevated pressures. But these are the kind of precious metal catalysts we are looking at, and the reaction is really quite simple. You have an alkene, such as this right here, okay, and you will hydrogenate it, right, by addition of literally H2. In this case, we're using platinum dioxide, and we're doing this in some sort of kind of solvent, in this case CH3CO2H. This is glacial acetic acid, right, if you're interested. It looks something like this. Okay, so again, here's our CH3, our COOH. Okay, so this is glacial acetic acid. But what this is doing is generating an alkene. With the hydrogens having specifically syn stereochemistry. Okay? And this is the reason why I put syn, because the hydrogens will have a very specific stereochemistry. So the reaction is stereospecific because there is a syn addition of hydrogen of H2, right? Again, it's hard to show the mechanism, but imagine this right here is the surface of the metal catalyst. And the first thing that occurs is that molecular H2 will go ahead and bind to the surface. So watch, now I have H and H bound to the surface of my metal catalyst. Again, my metal catalyst can be anything such as palladium on carbon, can be platinum dioxide or nickel. But this is the surface of the metal catalyst. Molecular hydrogen will adsorb to the surface. Then we will get my alkene. Okay. Let's show it this way. CH. It will adsorb to the surface. And when it adsorbs to the surface, a couple of things happens. This is a little more complex than we need to get to, but it uses its pi bond to essentially adsorb or complex to the metal ion, the metal atoms, I should say, sorry. First thing first is a hydrogen atom is transferred to one of the alkene carbon atoms, and that forms a partially reduced intermediate with a CH bond and a carbon metal sigma bond. Okay, so this will get transferred over, and we will generate kind of this, right? This is a carbon metal sigma bond right here. And then the second one is transferred from the metal to the second carbon, and this gives us our kind of alkene product. And then, of course, we break this carbon metal bond, and boom, boom, we leave the metal surface, as a fully kind of created alkane. Okay. All right. Boom, boom. Look at him. He's flying away. Okay. So again, you don't got to really worry about the mechanism here. Just understand that because the hydrogens are stuck on the surface like this, they have to add in a syn fashion. They cannot add in an anti fashion. Okay. So we can't have this forming because the hydrogens are literally on the surface. Okay. All right. So now you know that method. All right. And you know what? Actually, I'm going to leave this here for you. So you kind of have that. There you go. Okay. But do realize this could also be palladium on carbon, or, you know, something else. So this is a reduction reaction. Why is it reduction? Again, because we're adding hydrogen. Anytime you're adding a hydrogen, this is a reduction reaction. It is surface mediated, syn addition. You need a metal catalyst. We talked about the metal catalyst you need. We said it's stereospecific because it's a syn addition. It gives us a cis product when a cyclic alkene is reduced, for example, okay? In this specific case, we are getting a cis product, okay? Now, remember, you can use cis and trans terminology when it comes to a ring or an alkene, okay? So don't be thinking that, okay, just because this is an alkane, I can't use the word cis or trans, because I can. It is a ring system. In a cyclic system, you can use that. But yeah, so when a cyclic alkene is reduced, you get a cis product because you add at the same face of the cyclic system. And it is not considered a discrete reaction. The overall concerted reaction, the overall reaction is a concerted reaction on the surface. Okay, amazing. So now we have also taken a look at how to form a saturated alkene. The last thing that we have left is taking a look at how we form a diol and how do we form an aldehyde and a ketone. Okay, and these ones are kind of interesting because, you know, this is where we're really going to come back to a lot of these. So let's take a look at this. First things first is a reaction called epoxidation of an alkene. Epoxidation. So before I show you guys how to make a diol, I'm going to show you how to make something else called an epoxy. Okay, so an epoxy is a very special kind of cyclic ether, okay? It is extremely reactive because it is very strained, okay? So let's kind of show you reaction number 10. I believe this is number 10, yes. Epoxidation of an alkene, and there's two ways of doing this. There's two ways of doing this. One of them is from an alkene. The other one is from, again, let's write it down here for ourselves. One of them is from an alkene. The other is actually from a halohydrin. So I'll show you what I mean. One of them is from a halohydrin. So epoxidation of alkene. If I have an alkene such as this alkene right here, I can react this alkene with something called a peroxy acid in dichloromethane, and that gets me an epoxide. Okay? So reacting this with a peroxy acid, which, by the way, is RCO3H. This is a peroxy acid, Okay? It gets me a couple of things. So one is it gets me a regular acid, and it gets me an epoxide. That's my epoxide. Okay? The solvent of this reaction, dichloromethane, or CH2Cl2. Okay? Amazing. So, you know, what kind of peroxy acid do you use? There's two that you can really use. One of them is called MCPBA, and the other is peracetic acid. Okay. So MCPBA stands for metachloroperoxybenzoic acid. So the structure looks something like this, right? Benzoic, you know that there's a kind of a, benzene there. Meta referring to kind of substituents. So there's two substituents on the group. Metachloro refers to the fact that the chloro group is meta to the peroxybenzo group, right? So here is my OOH, okay? And this is it right here. Sorry about that. This is it right here. How do I know this? Well, because this is the ortho position. This is the ortho position. This is the meta position, and this is the para position, okay? So this is metachloroperoxybenzoic acid. This is in the meta position, okay? Amazing. So, that's MCPBA for you, and this right here is what we're interested in, the peroxo bond, okay? Peracetic acid looks like this, okay? So, boom, 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 or I'll just show it like this. So this is peracetic acid, okay? Again, you'd see that the same kind of peroxo bond is still there, so you could use either of these, but let's go ahead and take a look at the general mechanism for how this reaction works, okay? So the general mechanism looks something like this. Now, mind you, it is a little bit complicated, so I do warn you. But yeah, this is the kind of general mechanism. Okay, so we have our alkene, and let's draw our little peroxo bond. Here's my R. I'm just gonna do a generic RCO3H. Okay, so R, boom, 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 and H right there. So once again, how does this work? Well, first things first, this guy has to be deprotonated, okay? And when he gets deprotonated, guess what? We have this. Negatively charged, and so he is going to go ahead and do this, and this is going ahead and do that. All right, and so that's the thing that's actually forming our epoxide. But at the same time, this bond will break and come here. Okay. And that forms our nice little kind of epoxide. Mind you, these are all hydrogens, by the way. And that forms our epoxide. And, we have this leftover kind of thing. And what is that going to do? Well, that's going to be this, 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 this. it's going to undergo some kind of resonance. It doesn't really matter for our purposes, but this is kind of what it is, okay? Now, I do want to show you how this gets deprotonated, okay? So the way this gets deprotonated is like this. R, and you know, I can show it to you like this. HOO, boom, R. How does it get deprotonated? Okay, so first things first, this comes here, okay? And gets that. And now this will come and grab that, all right? And the bond will go here, and we will end up with that molecule. Okay, so actually, sorry, this should be this. Okay, there you go. And thus, the product that I end up getting is the epoxide and this O minus with the OH and the R. Okay, and just to kind of bring down the electrons and give us the nice resonance form, I will get O double bonded to OH R, right? And just like we mentioned, I get my acid, okay? Amazing. So I get my acid and I get my epoxide out of this. All right, so that is the kind of mechanism of how this is done, okay? Again, I don't really like the way I did this. Let's do it a bit more clean. So one more time, the epoxidation of an alkene starts like this. I have the H, I have the O, the carbonyl and R, okay? This goes up here. That gets me O minus, bound to my R, O, O, H. This comes and grabs this. This comes here, turns to this. This becomes O minus now. And it's bound to another O, which is bound to this, which is bound to an OH, R. I have my alkene here, okay? This will grab this, that will grab that, okay? This bond will end up coming here. And, you know, you can do a shorthand mechanism here, but I'm just going to show the full thing for the sake of completeness. We end up getting this forming for ourselves, right? Again, I had 1, 2 carbon. I still have 1, 2 carbon. Beautiful. And I get my O minus, right, with the OH and the R. I know that this can be a resonance structure. And the more significant resonance structure is when that comes down and forms our actual acid, OHR. Again, notice how this is just a COOH R. Okay, this is my carboxylic acid that forms. This is my epoxide, okay? So that's the mechanism for the epoxidation of an alkene. All right, you know, that's how it is, right? And again, it is stereospecific. Why is it stereospecific? It's stereospecific because, again, if you notice, just like we had our bromonium ion, right, forming, the bromonium ion formed like this, correct? Or in that case, like this, right? That was a syn kind of addition of the bromonium. Now, of course, that ring was broken eventually, okay? And that allowed for an anti-addition. But in this case, the ring is not being broken. The oxygen is being added to the same face, and it's not being broken. In fact, we're actually generating a ring product, and so this is a syn addition, okay? A syn addition of my oxygen, and that gives me a cis epoxide. Mind you, a trans alkene will give a trans epoxide, and a cis alkene gives a cis epoxide. So keep that in mind. Regioselectivity is not relevant here. And so, yeah. Yeah. Anyways, all of this, you know, the pi bond kind of attacking the electrophilic oxygen, right? Because mind you, that is electrophilic, okay? It is this oxygen that's attacked, not this. This is the electrophilic oxygen. The pi bond attacks it, okay? So yeah. Yeah. Anyways. Let's move on. The next method we're going to talk about is the base-induced formation of an epoxide from a halohydrin. Okay, so base-induced formation of epoxide from halohydrin. It's an intramolecular SN2 reaction, essentially. So how does this work? Well, you need a halohydrin, obviously. If you need a refresher, we made a halohydrin here. This was my halohydrin. So let's actually grab this halohydrin, copy it, and let's come all the way down here, paste it, and let's do our reaction with this specific halohydrin. Okay, keeping in mind that there is a hydrogen here and a hydrogen there. Okay, so remember, what alkene did we generate this from? That's a great question. What alkene did we generate this halohydrin from? Well, in this case, we can kind of go back and take a look, but you should be comfortable with the idea that this alkene was generated from a this halohydrin was generated from a trans alkene. How can you know that? Well, the bromine and the OH are on opposite sides of one another. Okay, so one of them might have this configuration and the other might have this. Okay, or, you know, it could be this or this. Okay, but either way, this is the case because they add from opposite sides, right? This has to open the ring from this side, and this adds on this side. Okay, and so they definitely are anti to one another. And because of that, it's a trans. Now, I shouldn't say that. The anti occurs regardless, but you should just be able to tell from that this comes from a trans alkene. So first things first, we get this from a trans alkene. Okay, or let me do this. So that comes from a trans alkene by way of adding Br2 in water. Okay, amazing. Next is we take this bad boy and by putting it in sodium hydroxide and water, because remember, this is a base-induced formation of an epoxide, we generate our very own epoxide. Now, how is this product going to look like? How do I know? Okay, let's take a look at the mechanism. We said it's an intramolecular SN2 mechanism. And SN2 mechanism occurs in one single step. Okay. So let's take a look. It is important, I think, for us to give it stereochemistry here. Let's do that. So, get the hydrogen there. Get our OH minus in there, base catalyzed, right? Or base induced, I guess, not catalyzed. We take this we generate this, and voila, I have myself a perfectly good O minus. Now this O minus, what it's going to do is going to attack this carbon here. Why is it attacking that carbon? Well, this carbon, remember, is bound to this bromine, and this bromine is pretty electronegative, so it's delta minus, and this carbon is delta plus. So this intramolecular reaction occurs. And by the way, intramolecular reactions occur faster than intermolecular reactions, okay? So that's one thing to keep in mind. And when this occurs, remember, the bromine becomes our leaving group, right? It takes the electrons with it. And so now we actually end up with this kind of product that has this with it, okay? There you go. And that's our epoxide right there, okay? And, you know, of course, this bond can rotate and turn into that, okay? But there you have it. There you have it. This reaction is an interesting one, right? Intramolecular substitution, halohydrin and a strong base required, aqueous and alcoholic base. Moderate heating may be needed. It is stereospecific because it's an SN2 displacement reaction. It's going to invert the configuration at the carbon bearing the leaving group. Okay, and what that means is that, you know, this hydrogen is here. It would have been like this, but now that hydrogen is actually going to become like this. Okay, it's simply just the way it works. It is going to invert the stereochemistry because of the fact that it's a backside attack. Okay, and you know, this is actually one of the reasons why this dude has to bend. And if you want, I can kind of put this like this and show you that this is what's going to happen, right? It's really not that deep, to be honest, but since we are showing, let's do that, okay? Amazing. All right, so that is how to make an epoxide without using an alkene. Of course, you could use an alkene, but you know, again, regioselectivity is not a factor here. The nucleophile and the leaving group are on adjacent carbons, so it's not really a concern. And so there's really two steps here. One is the deprotonation step. Second is the SN2. Okay? Nucleophilic displacement reaction. Okay, so now that we know this, amazing, we know how to make an epoxide. All right? I can either make the epoxide from the alkene itself by using metanchlorobenzoperoxy acid, or I can use peracetic acid, or I can make a halohydrin and then turn the halohydrin into an epoxide. But either way, what the hell can I do with this epoxide that I have created? Well, I can turn an epoxide into a diol. Okay, remember how I told you that we are going to learn how to make a diol from a alkene, and that is actually true. So we have to turn the alkene into an epoxy and the epoxy into a diol. Okay? And you can do this in two ways. You can have a syn or anti-diol. Okay? And we talked about that before. So reaction number 12 is going to be showing you how we get a syn or trans-diol. The trans-diol occurs with the ring opening of a protonated epoxide and anti-addition occurring. Okay? So let me describe to you what that means. Let's draw ourselves an epoxide. You know, it could be this epoxide, to be honest. It doesn't really matter. God. Doesn't really matter, to be honest. But essentially, we're going to, again, remember, epoxides are very reactive. This is acid opening, acid catalyzed opening. Acid cat opening of epoxide to transdiol. Again, you'll see why it has to be a transdiol, because the mechanism enforces it to be. So anytime you have an acid, of course, protonate something. Boom, boom, boom. I have the OH. It's positively charged now. What the heck am I going to do? Well, I have just generated a water. That water is going to come and open up the ring, right? Boom. And now I have one alcohol in this, and now I have one alcohol here. Note that this reaction is stereospecific. The attack occurs from the backside relative to this other OH, okay? What else? The reaction is also regiospecific. Remember, the water is attacking the more substituted carbon. Again, in this case, it doesn't really matter, but the water will attack the more substituted carbon, okay? So it is a Markovnikov orientation. But now I hope you can see why we get this transdiol or antidiol formation, right? These two are on the opposite sides of one another, okay? They're anti to one another, and this is actually what we would call a anti or transvicinal diol, okay? Vicinal, again, meaning they are adjacent carbons, all right? And you know, I of course I didn't show the deprotonation step, right? When this adds, it won't be OH, it would be OH2, and a water molecule will come and kind of grab this and do this, and of course then it will lead us to getting that OH and OH, okay? Beautiful, okay? So this is actually how that occurs, and of course in that process we generate our acid catalyst. Remember I said anything that is acid catalyzed, a catalyst has to be regenerated at the end of a reaction, otherwise it's not a true catalyst, okay? Amazing. And you know, protonating this actual epoxide, this epoxide already has a whole bunch of ring strain, but protonating it gives even more ring strain because, you know, well, don't worry about why, okay? The plus charge increases the ring strain even more. But water attacks at this point, opens the ring, deprotonation gives us the transdiol, and boom, okay? So in 3 steps, the reaction is protonation, nucleophilic attack, deprotonation. All right? Amazing. So that's one way. We go directly from an epoxide into a diol. Another way is I don't have to actually have an epoxide. I can actually just turn my alkene straight into a diol, but in this case it's a syn diol, and I would use what we call osmium tetroxide, and I'm not going to show you the mechanism for this one because it is extremely complicated. So in this case, we are going to use osmium tetroxide. So what does that look like? Well, again, if I have something like this with, you know, 2 methyls on the sides, I will use osmium tetroxide, which is this compound right here, in pyridine, which is a weak base. Okay. And, you know, I will do this in, and you know, there's 2 ways of doing this reaction. I'm going to show you the non-catalytic way, and I'll show you the catalytic way. Okay? So here's the non-catalytic way. All right? I'm going to use the non-catalytic way and show you that we can get this intermediate called an cyclic osmate intermediate. So watch. It will add across the double bond in this form. There you go. There's my osmate intermediate. Noticing that I have a CH3 on both of these sides again. And there's a reductive workup required when I use sodium HSO3 minus in aqueous solution. And it is precisely this aqueous solution portion that gets me this syn diol, okay? Again, my methyls are still there, okay? So again, the osmium tetroxide being added in there is kind of what's allowing me to get this syn addition of my two alcohols there, okay? There is another version I can do. I can use what we call a stoichiometric amount of a stoichiometric or catalytic amount of osmium tetroxide. So I use a very small amount of it. And I use a co-oxidant such as NMO, N-methylmorpholine, N-methylmorpholine N-oxide. So that's NMO right there. And the NMO essentially allows for the regeneration of the osmium tetroxide, okay, by the end of the reaction, okay? That's why we say it's a catalytic amount. So this stuff is really expensive, and if I'm not mistaken, osmium comes from space. That's like the only kind of source of it, so it's, you know, really expensive, and you do want to use this kind of thing. But you do get a vicinal syn diol. Whereas beforehand, with the epoxidation acid catalyzed opening of the epoxide, you get a trans or a anti-vicinal diol, okay? So again, a reductive workup in this reaction is required by this sodium HSO3. You can also do it in H2S if you would like, but, you know, the reaction is, of course, stereospecific. It's not regioselective, right? Both of the carbons receive an OH group, so of course not. Yeah. Oh, and by the way, this is a cyclic osmate ester, if you were curious. So yeah, this is it. One of the last reactions we're going to take a look at is ozonolysis and something called potassium permanganate or periodic acid, okay? So this is one of the last things we'll take a look at when we're talking about reactions of alkenes, right? This entire video was about reactions of alkenes. Okay, that didn't write, but it's reactions of alkenes, this entire video, right? We took a look at what the hell can we actually do with these alkenes, right? So we took a look at syn and anti-diols, epoxidations, and finally we're going to take a look at how is it that from an alkene we can make an aldehyde or a ketone. And again, for these last few, I'm not going to show you the mechanism because it is a difficult mechanism to cover. But one of them is called ozonolysis. Ozonolysis. And as you can imagine, it uses ozone or O3, right? So this is reaction number 14. And it is an oxidative cleavage reaction. So what the hell does that mean? So imagine you have this alkene, right? I have an alkene. And when I add ozone in dichloromethane at minus 78 degrees Celsius, I essentially cleave this bond. Okay, that's essentially what I'm doing in reality. I'm essentially just getting rid of that bond, and I am creating a ketone. Okay? Now, here's the thing. It gives you carbonyl compounds, but the double bond is split into a carbonyl fragment, and whatever the carbonyl fragment is dependent on the substitution pattern. Okay? So I'll give you a couple of examples, but this is going to get me a ketone. Okay? So let's kind of go through this example real quick. So what's going to happen is this is going to give you what we call a malazonide intermediate. So let me just kind of shrink this down, okay, and show it to you like this. Again, I have my alkene. I use ozone in dichloromethane and minus 78 degrees. And by the way, the way I get ozone is I just take oxygen, and by way of some electric discharge, I get my ozone, okay, and this ozone will then be used in this reaction. But anyways, what does the ozone actually do? So the ozone gives us this thing right here. It adds across our double bond to give us a malazonide intermediate. Okay, intermediate. And it gives us another thing, like throughout the course of the reaction, the malazonide intermediate will kind of rearrange itself to give us an ozonide. Okay, so that's where essentially you have this O, the carbon, and the O, and you still have your, bonds intact. So this is an ozonide. Okay. And again, you should kind of appreciate why we're not taking a look at the mechanism here. Now, using a zinc atom, we are going to, reduce this in glacial acetic acid or aqueous glacial acetic acid. Okay, so CH3COOH. Okay. Into our product. Again, in this case, because I told you we're essentially splitting this down the middle, we are going to get 2 ketones, okay? So 2 ketones are produced here, okay? But there are other cases. There are other kind of scenarios. So in this case, let's go through this reaction. Here, I have a molecule like this. I'm going to go through my ozonolysis reaction. Remember, this occurs in dichloromethane at minus 78 degrees Celsius, right? Just like we talked about over here. The second step was we needed zinc, okay, in some kind of acid. So, in the previous example, we used glacial acetic acid in water. You could just tell me hydronium ion. You could tell me HCl. It doesn't really matter. It doesn't really matter. You can use so many things, okay? Yeah. We're just going to keep it general and say hydronium. So what would this get me? Well, again, if we're cleaving this bond, we're going to get 2 ketones again, but the ketones that we get are going to be quite different. So we're going to get this ketone, right? This is a ketone, and we're going to get this ketone. Okay? So you see this became a ketone and this became a ketone. Okay? So again, we get acetone and cyclohexanone. Okay? The "-one" ending refers to the fact that we get 2 ketones. Now, again, there are other examples that we can do. So I took the liberty of going ahead and drawing this out here. because, this video is long enough as it is. But over here, we had scenarios where we had a completely substituted alkene, right? Meaning there was no hydrogens really left for us to kind of play with, right? But what if we only have a di substituted, okay? So it's only substituted once and twice. Well, then we only have, we have hydrogens to play with here. So in this case, when we cleave this alkene, what we're going to end up with is this fragment that has one hydrogen and this fragment that has one hydrogen on this side. So we're going to get one aldehyde and we're going to get another aldehyde, okay? Noticing that the kind of ester group that was here remains absolutely untouched. And this kind of shows a chemoselectivity of ozonolysis, where it's only kind of cleaving the alkene, and it's producing this 2-aldehyde product. Okay, so again, you really with ozonolysis get a carbonyl compound, but the carbonyl compound you get, whether ketone or aldehyde, really depends on your substitution pattern. Okay, so that's ozonolysis over there. Number 15, reaction 15, is going to be one of our last reactions. It's going to be oxidative cleavage again, but this time with potassium permanganate, so KMNO4, and periodic acid, where something like, something like potassium permanganate, right? If I take my alkene, depending again on the type of alkene you have, you will get different things. Okay, so for example, if you have something like this, this is a terminal alkene where we have two hydrogens kind of hanging out over there, and over here we only have one hydrogen. Correct? So a terminal alkene, such as this, the CH2 portion of it, once we reacted with KMNO4, okay, which by the way is acidic permanganate, so you have to have this in there, this will become CO2, okay, so this will leave as a CO2, and this portion will become a carboxylic acid, okay? So the entire product will look like this. 1, 2, 3, 4 carbons. So 1, 2, 3, 4. And my CO2. So this is what the cleavage, the oxidative cleavage of this compound with KMNO4 in acid gets me. Okay? It gets me, again, this specific portion gets me the carboxylic acid. This terminal part of the alkene gets me this CO2. Now, how might this differ? Again, remember, we can get either a ketone, a carboxylic acid, or a CO2. We can never get an aldehyde, from acidic permanganate reaction, but we can get a ketone, a carboxylic acid, or a CO2. Whereas comparing it to ozonolysis, in ozonolysis I can either get a ketone or an aldehyde. Okay, so we know one way of making a carboxylic acid now. Actually, this is amazing. Let's write this down for ourselves. In our reaction little toolbox there, we can make a carboxylic acid as well, by way of KMNO4, aldehyde and ketone. Ozonolysis, KMNO4 as well, right? Although that's just for the ketone. Okay, now let's try a different compound, a different alkene, if you will. Let's do this. What would this get me? What would this get me? Well, I would cleave this bond, again, KMNO4 in hydronium. Okay, and what this would essentially give me, right, is if I open the ring, is it will give me two ketones. Okay, why will it give me two ketones? Because it is fully substituted. There are no hydrogens for me to play with. If there's one hydrogen, I will end up getting a carboxylic acid. That is actually the reason why I don't get an aldehyde, right? If you remember in ozonolysis, one hydrogen resulted in what? An aldehyde, right? Two hydrogen resulted in an aldehyde, okay? We see that here. One hydrogen gets an aldehyde. But in this one hydrogen will not result in an aldehyde. In fact, it will give me a carboxylic acid, and two hydrogens would give me a CO2. Whereas if there are no hydrogens, I will just generate two ketones, and here is the fully extended kind of length of it. I will get two ketones, okay? So one here and one here. If you're confused, this is that portion and this is this portion. Okay, this is just kind of opening up and unwinding the ring after I cleave this bond. Okay, all right. So last one I want to talk to you guys about, number 16, is oxidative cleavage. So again, all of these have been oxidative cleavages. Oxidative cleavage, and ozonolysis is another oxidative cleavage. And in both of these, we've actually worked with a, with an alkene. In this scenario, we're going to work with something called periodic acid, so HiO4, periodic acid, and in periodic acid, I can get either an aldehyde or a ketone, again, depending on my substitution pattern. But the way this occurs is a little bit different. So I actually start out from a diol, and not just any diol, a syn diol. Okay, so, we remember that we had a method of synthesizing a syn diol. If you remember, we talked about a trans diol formation. A cis diol we made from an alkene being reacted with osmium tetroxide, okay, in NMO. Okay, again, if we scroll back up, here is my, I don't know if this was earlier. There it is. Here it is, my osmium tetroxide and pyridine and NMO for the catalytic version. And of course, I would use HSO3 at the end in water, and that would give me a syn diol. So what do I do with the syn diol now? Well, here is my syn diol, OH, OH, and what periodic acid is going to do in THF and water, so aqueous THF, is it's going to add across these alcohols and essentially cleave it down the middle. Okay? Now, why does this matter? Well, let's add a couple more substituents to our product. Let's say this is a hydrogen and this is a methyl group. If I were to cut straight down here, because this is an OH and there's another carbon here, this region will end up becoming a ketone. And because this region only has a hydrogen, it will end up being an aldehyde. So to show you, let me just show you the intermediate very quickly. Of course, the iodine would add here, and of course it would have 3, and there you go. That's my periodic acid. There is one more thing. Let's do this. The oxidative cleavage, like I said, it would get me. This is the methyl, right? If you guys remember, this was the hydrogen. This was my 2 OHs. So if I cut this down, I actually end up generating a ketone here, right? This is my ketone. And on this side, I end up generating an aldehyde. And again, you can do exactly what I did in the kind of previous one, where you can turn it into its open chain, fully stretched out form. But you can see I get a ketone and an aldehyde, again, depending on the substitution pattern of my starting compound. And in this case, if I do something like this, boom, 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 boom. Let's actually do this. And let's link these as such together. Boom. Boom, boom, boom. And let's say that they both have OHs here. Okay. If I put this through another periodic acid in aqueous THF reaction, this would generate me what? Well, you have to remember, I am essentially cutting this bond here. Do I see a hydrogen on either end of this? I don't see a hydrogen. All I see is carbons. And so when I cut these two, look at what's going to happen. I will cut this. I will separate these for you. This will essentially become a ketone, and this will essentially become a ketone. Okay? So my products from this reaction will end up being two ketones. And if you're curious, this is cyclopentanone. So I will get two cyclopentanones from a syn diol. Okay, a syn vicinal diol. All right. And so now we have learned all of these reactions. So let's, again, kind of for our own peace of mind, summarize what we can do with an alkene. Okay, we can turn the alkene into an alkyl halide by way of adding HX. I can turn it into a saturated alkane via syn addition by metal catalyst reduction, okay, or hydrogenation, if you will, H2. I can turn the alkene into halohydrin, and the way I do that is by adding Br2 or Cl2 in water. I can just get a dihalide, okay, and that's by adding Br2. I can get an epoxy, okay, and I can do this in two ways, actually. I can do metachlorobenzoperoxic acid by this actual alkene, or I can get my halohydrin to turn into an epoxy by way of an intramolecular SN2 reaction. So I will actually deprotonate one of my halohydrins, okay? So by way of base induced, if you will. Base induced SN intramolecular SN2. SN2, and if you remember, we took a look at the mechanism somewhere. There it is, base-induced formation of epoxide. Okay, so let's again summarize for ourselves this kind of epoxide. What else am I missing here? Oh, of course, we can make an alcohol, and we saw 3 ways of making an alcohol. We saw a couple of ways of making a diol. We saw how to make an aldehyde. We saw how to make a ketone. We saw how to make a carboxylic acid. Okay. We said that a diol could be syn, or it could be a trans diol. And the syn diol, we said that we're making the syn diol from alkene and osmium tetroxide. we can make the transdiol from an epoxide. So let's actually show that. Transdiol from an epoxide, right? Let's see. Yes. Transdiol from an epoxide by acid catalyzed ring opening. So acid cat ring open, ring opening. Another way is, we talked about alcohols a lot, actually. Alcohols. We said there was 3 ways of making an alcohol. One is the acid catalyzed hydration. So acid catalyzed hydration. We said that the second method was oxymercuration. We said that the third method was actually getting a syn hydroboration oxidation. Okay. Then we were talking about a diol. We talked about diols. How do we make aldehydes? There's a couple of ways you can make an aldehyde. You can either do ozonolysis. Ozonolysis gets you an aldehyde. Or you can do from a syn diol, you can get an aldehyde by periodate. Okay. What else can you do? You can get an alkene. You can get a ketone. How can you get a ketone? You can get a ketone by a couple of methods. One of them is ozonolysis. The other method is KMNO4, which, if you remember, we said KMNO4 can give you a carboxylic acid, a CO2, or a ketone. So we will write that down for ourselves for KMNO4, right? Man, what else? That's pretty much it, to be honest. That's pretty much it. So again, we covered a lot of reactions. We also covered some reverse reactions as well. If you remember, we said that we can turn an alkyl halide back into an alkene by dehydrohalogenation. And we took a look at the mechanism for that, right? It was this was obviously done with acid. Let me kind of find, there it is. So dehydrohalogenation in acid, right? We said this is a kind of E2, E1 mechanism. It was an elimination in general. We said going back from an alcohol is acid catalyzed dehydration. Okay. It's really important because acid, and this is a point that I should have brought up earlier, when we're talking about dehydration of an alcohol and we start talking about H2SO4 and water, it's important to understand that it is really not concentrated sulfuric acid, okay? So concentrated sulfuric acid is required for acid catalyzed hydration of an alkene, okay? Strong acid catalyst is required, and concentrated acid at high temperatures. But over here, it is small amounts or catalytic amounts of acid required for dehydration. So that's actually important. And the same goes for the alkyl halide, right? Okay, so again, we took a lot of these, took a look at a lot of these kind of reactions. I will erase this, and just for us to kind of understand that there are so many reactions we took a look at here, and you know, you can go through all kind of 16 reactions we took a look at here today. Next video is going to cover the reactions of alkynes. You will find a lot of similarities there, and I'll see you there.